Hello everybody. Let us resume our discussion today. We have studied the postulates of quantum mechanics, and let me first review them. The first postulate told us that it is the wave function which has information about the state of the system, and we can calculate the probability of finding the particle between x and x plus dx in the following way. And this is integrated over all space, all x in this case. Remember that we are doing one position dimensional quantum mechanics with only one particle for the time being at least. Now, this demanded that both psi and del psi del x need to be continuous, and many other things I'm not. So they has to be finite at all points, and also that this integral should not diverge. So let's not go through all of them again, but you can refer to your notes from the last class. Sometimes we introduce the concept of a normalized wave function. So if the wave function, if I get a function which is wave function which is normalized, it essentially means that this integral in the denominator is equals to 1. So I don't need to write the integral explicitly all the time. So this integral is 1. So if I give you any function which is not normalized, you can find a normalized wave function out of it, just calculating in that this integral and set it to 1. Also, let us ask the question that what is the dimension of psi? We can calculate that from this integral itself. You see, I have two psi's here, so psi dimension of psi square, and then I have a length dimension here. This should be equals to 1. Now this is for one dimension. As you can imagine, if I would have had 3 dimension, then I will have dx, dy, dz, all three of them. So this L will not be L, then it will be L cube, because I have to integrate over the volume. So the length cube is a dimension of volume. So let me write it like this, where d is the dimension. In the problem. So in our case, it will always be 1. So if d equals to 1, which is the cases we will always deal with, that dimensionality of psi then comes out to be L to the minus half. Okay, so 1 L to the minus half here, 1 L to the minus half here, 1 by L times L gives you dimensionless 1. So this was all about the first postulate, and a little bit I have added here. The second postulate, remember that all dynamical variables were uplifted to operators. So for each dynamical variable, there is one operator, and remember that we said that if A is the dynamical variable, the operator is A, we write A hat, and if the system is in the eigenstate of A, then it will satisfy this equation, which we call the eigenvalue equation. And then we talked about several operators. So say position operator, so x cap, momentum operator minus I h cross del del x, energy operator I h cross del del t, etc. Let me tell you that, say we have a variable dynamical variable I mean dynamical variable, say it is fx, function of x, and all these, so by the way, these operators, the form of these operators when psi in position space is written in position space. If it is written in, say, momentum space, this operator forms will be different. This is only for psi in position space. So say I have a dynamical variable which is f of x, so it can be x or can be x square, etc. The operator corresponding to this dynamical variable I can find just by doing f of x cap. So for example, if it is x squared, I will just have x cap squared. So example, if the dynamical variable is x squared, so what all I have to do is I have to do x cap times x cap on psi. And that is essentially, this is often written as x cap squared. Remember last time, another example, last time when you say p square, so we wrote this as minus ih cross del del x square, which is minus h cross square del to del x2. Okay, so this was about the operators, and then we said that before any observation, the psi is, I mean, nobody knows what it is. If you wish to write it in terms of any eigenstate, you can write it in this way. Here C are some constants, and so this can be written this way in terms of the eigenfunctions. And we also mentioned that the eigenfunctions of a given operator is always orthogonal. So this is delta mn. Remember that delta mn is 1 when m equals to n, otherwise it is 0. Okay, so when we do measurement, psi collapses to one of the eigenstate of the operator which you are measuring. Then we set expectation value of any operator is the quantity that you can predict. This essentially means is that if I do this measurement many times, what is the average value that I will get? So all these integrals, I am writing a little shorthand. So all this integral is over all space. So this is the definition of the expectation value. The integrals are over all space. Let me repeat again. And psi is a function of x and t both. I am not writing explicitly. So this is the average value, and we have just learned that if I want to calculate the expectation value of x square, what all I do is a cap square. So I can say, if I we are talking about uncertainty the other day, so I can calculate the uncertainty in x. So let's call it delta a, in a, sorry, in the measurement of the dynamical variable a, and this will be given by a cap square expectation value minus expectation value of a cap square. Okay, so when you try to calculate the expectation value of a cap square, what all you have to do is you have to introduce another a cap in between. So a cap into a cap phi. So now you know, if I give you the wave function, how to calculate the dynamical, how to calculate the expectation value of the wave function. Sorry, how to calculate the expectation value of any dynamical variable, and also the uncertainty associated with that measurement. Okay, so let's take an example. So let's say that, so obviously this is something that is not known prior to the measurement, but say that I know everything. So let's say, just for fun, that this is there in the eigenstates of energy in terms of, so I'll measure energy. So in terms of eigenstate of energy, somehow this psi is given like this. So there are only two energy eigenstates in which there are non-zero values of c's. There may be other energy eigenstates where it is zero. Somehow it is kept like this. Okay. So then what happens to the expectation value of energy? Let us ask that question. So what is the expectation value of energy here? So let's calculate. How will I calculate? Well, I have to write here dx psi star, and psi star is star of this entire thing. So C1 star psi E1. Let me not write the functional dependence to save space. Psi E1 star C2 star psi E2 star. That is just the psi star, this part. Then I have a cap. A cap is nothing but the energy is E cap. Let's write just E cap. And then psi again, which is C1 psi E1 plus C2 psi E2. In the denominator, I have almost the same thing without the expectation value. All right. Now, let's look at the integration in the denominator first. So let's look at this integration. So let's call this denominator. So say re. Okay. So I have four terms to integrate. C1 star E1 times this. So if I do that integration, so let's write the first integration. So this is C1 star times C1, and then psi E1 star psi E1. What is this integration value? You see, I have this in C1, and C1 is constant. C1 star is also constant. That will just go out of the integration. The integration I have to do is on this quantity. So this is like psi 1 star psi 1. And we saw that if we are doing such integration, if m on n equals to same, the integral value is just 1. This is because of the orthonormality condition. So this will give me C1 mod square. Then I will get another term. So I will just write two terms here. The rest you can write. So C1 star, and then I will get C2. So this one and this one. So psi E1 star psi E2. Okay, and then I will have another term and the fourth term. So you'll see that once we know how to calculate this term, we can do the rest too easily. So here we see that I have one eigenfunction here, the other eigenfunction here. Again, for the orthonormality, now m and n are different of the delta mn. So this term is 0. So this term will not contribute. Similarly, when I do C2 here and C1 here, they will not contribute. The only thing other will contribute is both of them C2, and that will give you C2 mod square. Okay, so that is, now I know how to calculate the denominator. Denominator is just the mod square of C1 and mod square of C2 added together. What about the numerator? Well, let us again look at term by term. If I look at the first term is dx C1 star psi E1 star, and then I have E cap C1. C1 is just again just a number. E cap operating on psi E1 eigenvalue equation will give me E1, the energy, corresponding energy, and then psi E1. Okay, so let's not call this the numerator. So let's calculate this term first. So what will this term be now? You see again the same integral will happen between these three terms, and that will just give me 1. So I will get E1 mod C1 square. Just like the denominator, if I hit E1 here and E2 here, or E2 here and E1 here, both of these terms will be 0. So the numerator, you can now try to work out yourself, will be E1 mod C1 square plus E2 mod C2 square. So expectation value of the energy is E1 C1 mod square by C1 mod square plus C2 mod square plus E2 C2 mod square Well, there's something remarkable here. Now I can understand what are these quantities C1 and C2. Because here if I look at what it is telling you, the denominator is the total probability. The denominator is essentially psi star psi integral dx. So it's the total probability, which is always 1. And the numerator then should be telling you what is the probability of finding E1, and this is this thing telling you what is the probability of finding the energy E2. So if I say C1 square, so let's say C1 mod square is 1 by 4 and C2 mod square has to be 3 by 4. It means essentially that if I do this experiment 400 times, 100 times I will get the energy E1, and 300 times the wave function will collapse with the energy E2. Okay, so this is the meaning of these coefficients C1 and C2. They essentially gives you what is the probability of finding that particular state, that particular energy state in this example. Okay, so this is about the fourth postulate and some extension of that. In the fifth postulate, we got to the Schrodinger equation. So let me write that down. And again, this is only for one dimension. Just like I have del 2 psi del x2 here, I will have del 2 psi del x2 plus del 2 psi del y2 plus del 2 psi del z2 if it is a three-dimensional case. But nevertheless, we have one-dimensional case here and times psi. And remember, psi is a function of both x and t. I'm not writing it explicitly here. Now, in this expression, remember psi is also a complex number, right? Psi has to be a complex function. The potential, which is the physical potential, is real, because in classically we deal with all real quantities. This potential is essentially the same potential as in the classical mechanics, and I should have written v x cap over here, but as we know that the in the position representation x cap, uh, the operator for x cap is x itself. The position operator x cap is x itself. This is py cap, this is e cap, so I don't need to write it explicitly. So vx cap is essentially vx. If I take a complex conjugate of this equation, so I will become minus I, psi will become psi. So complex conjugate I write with the star, right? Here I will get h cross square by 2m del 2 psi star del x2. Remember v is real again, so v will remain v, and then psi star. Okay. So before we go further, let us calculate one quantity which will be useful later. So I have this probability density function. So let us write that psi is normalized. Okay. What do I mean by that? Psi star psi integrated over all x is 1. So psi is normalized. So which means that this is 1. So the denominator in this expression of p, the probability density, so this is probability density. The denominator is 1, so I can just write p as psi star psi. So let's do that. Psi is normalized, so p xt is just psi star psi. Okay. What we want to do is we want to find out the time rate of change of this p, this row. Sorry, p. We call it p. So that you will agree that this is del t of psi star psi. Just from its definition. Now del t of psi star psi I can write like psi star del psi del t. Kill one, leave the other to be killed later, like now psi. Let's keep the order proper, so it doesn't matter. So this. Okay. Now let us calculate I h cross del p del t here, which means I multiply both of these by I h cross, and I h cross del psi del t I can replace the right hand side from the Schrodinger equation. So this becomes psi star I h cross del psi del t is minus h cross square by 2m del 2 psi del x2 plus v xt psi. And then when I do for this, del psi star psi I can replace from here, but now I have to take care of that minus sign. So there will be minus psi by 2m, and now these will be all psi star. If I look at the right hand side, this term is v psi star psi. This term is also v psi star psi with a minus sign. So they will cancel out. So let's see what will I get in terms of del p del t. So del p del t, one h cross will cancel out from both sides. The other will remain. So del p del t I should be able to write in like minus h cross by 2m, and I put the I in the denominator. Okay, so let's see. So IH cross I have put in the denominator. I have taken the term with the minus sign here, which means I will get the first term, which is psi star del 2 psi del x2, and then I get psi del 2 psi star del x2. All right. Now let us define something. Let us define this quantity which I call Jx. This is h cross by 2mi psi del psi del x minus psi del psi star del x. Okay, so let us call this for the time being as current density, and we'll come back to why it is called current density. But let us define my current density like this. Okay, this is the definition. There's a reason why it is called current density, but let's call this Jx. So you can imagine that instead of x, if I want to write Jy, so all these x's will change to y. That is how I will write Jy. But for us, it is only one dimensional, so we can just deal with this. Now, what is del Jx del x? So del Jx del x, if you forget about the okay, let's write. So h cross by 2mi. So I'll get psi star del 2 psi del x2, and then I will get plus del psi star del x and del psi del x. And when I do this, I will get psi minus del psi star del 2 psi star del x2 and minus del psi star del x del psi del x. And again you see that this cancels out. So what I get is essentially whatever I have here with a minus sign. So this, in terms of this, I can now just write del p del t plus del jx del t, del jx del x equals 0. Okay. So let's ask the question, what is the dimension of J? So Jx is h cross by m, and then I have psi square and the length dimension, because I have del x over here. Two psi's in the upstairs and length dimension. Now you know already that. Okay, so an easier way to calculate what do you expect the dimension to be is to remember that this term minus h cross square by 2m del 2 psi del x2 has the dimension of energy, right? No, okay. So let's do it in the right way. So this, if I write, h cross has the dimension of angular momentum. Angular momentum means it has one length and then a velocity and obviously mass. Denominator, I have one mass. Let's see, what is psi square? Psi, if you remember, we worked on its dimension. It had a dimension of L to the minus half. So this is L to the minus 1, and I have another L in the denominator. So the Jx, what dimension is left for it? So M cancels out, one L cancel out here. So it has a dimension of T inverse, but let us write that as 1 by L times LT inverse. We'll see why. See, LT inverse is like velocity. It is the dimension of velocity. And 1 by L is nothing but, this is the dimension of P. P is the probability density, because remember that if I integrate it over L, then LL cancel out, I will get it dimensionless. So this Jx is like density times velocity. Okay. Now obviously the density is taken as per unit length here. In a real situation, it will be considered as per unit volume. So just remember that it has the dimension of density times velocity. Okay. So what this equation is telling you is that if I am dealing with a small volume, so say I am dealing with a small volume, fixed volume in space, if I ask the question, what is the rate of change of probability density in this volume? The probability density rate of change with time is in the left hand side of this, or in the first term is this. The probability density only changes if the current, and this is not any current, is called the probability current density. So the rate of change, time rate of change of the probability density is because of the flux or the change in the probability current with function as a function of x, which is essentially means that it's called the flux of probability current. Means it's a current, which means that something must be going out of this volume or coming in this volume. So some quantity related to the probability may have to go out of the volume or come into the volume such that the probability current in that volume changes. Sorry, probability density in that volume changes. Okay, so we'll come back to this concept of J later, where in a calculation. That's why I wanted to introduce it to you here. But that's it. That's the discussion we'll have about it. Let us go back to our Schrodinger equation. Remember that Schrodinger equation we achieved from the fact that we said that the energy is kind of given by the Hamiltonian, which is written by P square by 2m, plus potential. The potential in general can be a function of x and t. In that case, the energy will be a function of time. And so that we could not derive, nobody can derive Schrodinger equation, but we can arrive at it. We can argue that, okay, so this is the equation that we will try. And you remember that when I say talk about principles in physics, any of the principle of physics, they cannot be derived. They are just assumptions. Once they start explaining using the principles, we can figure out, we can explain what is happening around us. Then we call them principles. So before we can explain, they are just assumptions. Okay, so this is the Schrodinger equation. So we'll consider a very particular case of the Schrodinger equation, which are known as stationary states. And this is the only thing that we will deal with in our rest of our lectures. So what is a stationary state? It is the case where V potential is not a function of time. So it's only a function of x, not a function of time. Okay. So in this case, one can simplify the Schrodinger equation. So in this case, psi as a function of x and t can be written as only a function of x. So this is capital psi, only a function of x, multiplied by something which is only a function of time. So let's call that function of time as phi. So I can now replace this in my Schrodinger equation. You see what happens here? It's del psi del t. So I take the time derivative of this. When I take time derivative of this, obviously this part comes out because it's a partial derivative. So I can write this outside. And here I get del phi del t. Now I don't need to even write del phi del t because you see phi is only function of time. So this is a total derivative of time. Okay, but still, okay, so let's still write the partial derivative. Just remember that it's only a function of time, phi. There is a reason for doing that, but I will not go into it. What happens in the right hand side? Just like psi came out here, the right hand side there is no time derivative, so phi will come out from the right hand side, and then the rest I can write h cross square by 2m del to this capital psi del x2 plus potential, which is a function of x only, so I am just writing it Vx, and then again that capital psi. Okay, let's rearrange these a little bit. So I write IH cross del phi del t and put that phi from the right hand side to the left hand side. And in the right hand side, then what is left is minus h cross square by 2m del to capital psi del x2 plus Vx capital psi, and that capital psi which was there in the left hand side in the previous equation comes in the denominator here. Okay. Now something remarkably has happened. If you look at the left hand side here, it's only a function of t, only a function of time, and this is only function of x. So left hand side does not depend on x, right hand side does not depend on time. So if I give you two functions which are equal, but the left hand side doesn't depend on x and the right hand side doesn't depend on time, the only thing they can be at best equals to is a constant, which I call energy, a constant. Constant means independent of both x and t. So this method is called method of separation of variable. And you see, if v was a function of t also, it would not have been possible because here I will get a time dependence. But that is not the case we are dealing with. We are dealing with stationary states, which are the cases where v is not a function of t. So I get IH cross del phi del t equals E phi and minus h cross square by 2m del 2 psi del x2 plus v function of x capital psi equals also e capital psi. You can solve this readily, and a possible solution for this is some phi 0 e to the minus e t by h cross. You can just put this in this equation and you will see that it satisfies. And immediately you know now why I am calling it E, because if I operate phi with the energy operator, this give me E phi. You can try that out. If I operate phi with the energy operator is, let's try it out. So IH cross del del T operating on phi, which is phi 0 e to the minus I et by h cross. I'll get IH cross. Once I do the differentiation, I will get IE by h cross. And I will get phi 0 e to the minus IET by h cross back. And this you will agree is equals to E. Okay, so that is all right. The right hand side I can write like del 2. I cannot do much if I do not know what is Vx, but I can write this as plus 2m by h cross square Okay, so to solve this, I need to know what is V. To solve, we need to know what is V. Also remember that psi and psi prime, the first derivative of psi with respect to x, both are continuous, supposed to be continuous. And what else? They're finite at all x, so they're finite at x tends to infinity. So there actually has to be 0 at x tends to infinity. So that is our condition. Now let us write down this thing completely. So this is this psi xt for the stationary states is then given by this psi as a function of x. Remember that when we wrote down this constant phi 0 here, it essentially constant means that it doesn't depend on t. It depends on x, and that x dependence is essentially that capital psi x. So my psi xt is minus I et by h cross. This is for stationary states. So why is it called stationary states? So let's ask the question why it is called stationary states. It's called stationary state for the following reason. So let's try to calculate the expectation value of any operator A. Okay, how do I calculate it? And say my wave function is normalized, so I don't need to bother about the denominator. I'm just writing, so normalized psi. So I'm just writing the numerator. The numerator is psi star a cap psi dx. So how should I write psi star? Psi star I should write in terms of, now I will write in terms of these wave functions. Now when I write this is true for a given value of energy. So say that value of energy is En, then this will be the corresponding psi n, and this I can also write psi n. Why is that true? Because you see, this all of these has to have the suffix n. So once I have the suffix n here, the solution that I get for capital psi will also have the suffix n. Similarly here. So this essentially is, so I have a summation over n cn star psi n star. So this is capital psi x e to the minus becomes plus now because it's star en t by h cross. So this entire thing is my psi n. So and then psi n and then integrated over summation over all n. Remember that we needed that. So then I have a cap and I need to write the same summation again. So now say over m, and I don't have any star now. This is again capital psi x e to the minus I e m t by h cross. Okay. What all we are doing here is what we were doing for that example of energy. So this is the energy operator sitting here, and then these are only C1 and C2. Now we have said that we are summing over many C's. So that's why I have written a summation. And instead of the energy operator, because we are calculating the expectation value of A, I have kept the A operator. Okay, now you see what is happening here. So if I do write down this integral, remember that this will only be true for m equals to n. So let us do it for the energy operator only, because otherwise I need to tell you a little bit more, which I don't want to tell you right now. So let's calculate for the energy operator only, but this will be true for other things also. So say the energy operator only. So this is E cap and E cap. Okay. So what will happen once I operate with the energy operator in the right hand side? So I'll get this summation over n, and then I will have this summation over m. And let me write the integral later. The integral is operating only on x, right? It is nothing on integral on summations, obviously. So I'll have Cn star, I have Cm, and then when I operate E on psi m, I will get Em, which is the energy, and I will get back psi. Also, these exponential parts are independent of the position x, so I can just take them outside the integral. And after this, I have just the integral of dx psi n star psi m. This, you remember from the orthogonality, is delta mn, and that means that these summations are 0 if m is not equals to n. So again, remember that I will, just like previously I had C1 plus C2 and C1 star plus C2 star, the cross terms where one has 1, the other has 2, they are all 0. So here I will just get the same terms, so n equals to n terms, so this will make this square. I will get Em again, En again, so m equals to n. But remarkably, because n and m are same, En and Em are same, this just becomes e to the 0. So the expectation value of the energy as I calculate here is just this. So this is independent of time. And this is why we call it a stationary state. So this is true for expectation value of any other operator. So if you calculate the expectation value of a given operator for these type of states, which we call the stationary states, the same will be true for all time. The expectation value of the energy or any operator will be true for all time. So you have to just calculate it once. So if the potential is independent of time, then this is what comes out. Okay. In the rest of the discussion today, let's see what we have to do now. Remember that to work with quantum mechanics, any system, so let me write it down. Any system defined by V, and now we will deal with only stationary states, so Vx, solve. So this equation, which is minus h cross square by 2m del 2 psi del x2 plus v only x, and then psi again equals to e psi. This is often called the time independent Schrodinger equation, just because the psi is independent here. This is just a name used in some of the literature, so I just wanted to make you familiar with this name. So any problem this, I solve this for a given E. We'll see at certain cases, we may find that only some values of E's are preferred, the other E's, not continuous values of E's are preferred, only some discrete values of E's are preferred, energies are preferred. So those will be the energy, discrete energy eigenstates. So any function V, you solve for this. So this is, once I solve for this, I can get expectation value of any operator from psi. And I calculate it once, I am done, because it doesn't change with time. Okay, this is the procedure that one follows. Now, we'll do one more simplification here. We will work with only a very particular type of potential in the rest of the course. And these are called piecewise, constant potential. Piecewise constant potential. What do I mean? So let me try to draw such a potential. So this is my x-axis. In the y-axis is the value of the potential, V as a function of x. Okay. So what it means is that I may divide my x into certain regions like this, and I say that my potential is constant in this region, say let's call it V1, and here it is a different value, but again it's a constant value to here, say, and here it has a different value, again it's a constant value. Okay, so within this region the potential doesn't change, and remember that these are the boundaries of this region. So within this region, if the potential doesn't change, then the solution of these equations within this region will assume a certain functional form. So say I calculate that the corresponding solution in this region is psi1, in this region is psi2, in this region is psi3. If you wish, there can be something else here, psi4. And then what all I have to do is, at these boundaries, I need to make sure that psi and del psi del x continuous at the boundary. And once I make that sure, then I will get a psi which gives me the potential at everywhere. Okay, so now there is a simplification that happens to this equation, or the way we wrote it down before. So here we wrote down the equation 2m by h cross square E minus V. So let me write it down again here. For such potential, And psi is a function of x only, so I can just write d also. So this is d2 psi by dx2 plus 2m by h cross square e minus vx psi. And what has happened is that vx is not vx anymore, it's just a constant v0, right? So if I say that this particle has energy E, which is moving in such a potential, and say maybe this is the energy E, sometimes this energy is greater than V, like here, sometimes it is lesser than the potential. Okay, so we have to just consider what happens if E is greater than V0. Then you see that E minus V0 is greater than 0. We can say, just for simplicity, we can define this as k square. Then this equation is just d2 psi dx2 plus k square psi, or let's say k1, equals 0. What is the solution? You know quite well that this psi will be some constant times e to the I k1x plus some other constant times e to the minus I k1x. And the only other option that you can have is E lesser than V0. So E minus V0 is now lesser than 0, E less than V0. So this, let us call this K2. So this is like K2 square psi. Okay. So K2 square is 2m by h cross square V0 minus E now. And this equals to 0. And you know that this has exponential solutions without the I. So let's call C e to the k2x and d e to the minus k2x. Okay. So these will be the forms of the solution, and then the boundaries, like for example, you can see now here it will have oscillatory solution e to the ikx type of solution. Here it will have e to the kx type of solutions. And then in the boundary you have to match this. So this is all we have to do. Okay, so we'll look at problems, real problems from tomorrow onwards. Let us stop our discussion here today. We have looked at the postulates of quantum mechanics and how to work with the postulates in a little bit more detail today. Thank you.